Давайте продолжим. So here you see again the summary of qubits which we talked about in the previous lectures. We discussed the charge qubit, we did historically the first one. We also discussed the flux qubit and the phase qubit. And last week we were busy with transmons and continued also this week. And the last topic of discussion of today was about fluxonium, which came up as a suggestion of alternative platform to transmons. I should mention that actually nearly all companies which develop superconducting quantum processors, like IBM, Google, Rigetti, and others, they follow they use transmon as the major type of qubit. There are only a few groups in the world which proceed with fluxonium, and between them is also our group at Mises. And where last year we have been able to show really top quality 2-qubit gates. The competitors there is also Lab and Alibaba company, obviously Chinese company, which also has a base in the US and has two groups working in China and in the US correspondingly, and few others. So this competition is going on, and it's still not clear which qubit will be the qubit of choice in the future. But still, the advantages of particular platform are being explored for a variety of interesting experiments. Now, let's look a bit from a bit more general perspective on the fluxonium qubit. If we start from a transmon qubit, what we have typically is a tunable Josephson junction which has a squid, and the junction then has energy levels 0, 1, being transition being slightly larger than transition between 1 and 2. And here on the left plot, you see the picture for symmetric transmon, where you have two identical Josephson junctions. And blue line shows the transition 0 and 1, and this dashed line shows the transition between 1 and 2 for this particular parameters. Now, if one makes the transmon asymmetric, we discussed this also briefly last week, such that the critical current of one of the junctions is a bit larger than the other, then this modulation curve as a function of magnetic flux doesn't go to 0 at half flux quantum, but actually goes to another minimum or another extremum, and the enharmonicity preserves. So this is dashed line also follows the curve of the 0-1 transition. For C-shunted flux qubit, something which we didn't discuss specifically, but what also exists, basically it's a flux qubit which has additional shunt, capacitive shunt here, making the charge noise less critical for the device, has the dependence on the magnetic flux, which is shown here. And interestingly, the transition 1, 2 actually becomes at frequency a bit larger than the frequency 0, 1 at half flux quantum. And moreover, this behavior is emphasized also in the fluxonium device, which has additional capacitive shunt, where the harmonicity is actually inverse compared to the transmon. So you see the harmonicity is here is negative. So 0-1 transition has a larger frequency than 1-2. So unharmonicity is negative. Here, unharmonicity becomes positive. And that's quite interesting, and also can be practically useful for implementing more precise 2-qubit gates. How and why exactly, this we discuss a bit later. So the classification of superconducting qubits can be looked up in different ways. So this is the picture from the review paper. in physics reports, which is one of possible reviews to look up. So there could be different names, of course. So there is a X-mon or transmon, there is a fluxonium, there is so-called G-mon, where you have a tunable Josephson junction current, something which is realized with semiconductor nanowire, which is controlled by electric gate. There are also simple flux qubits such as three-junction flux qubit, also the capacitively shunted flux qubit, where you have additional capacitance, and also the tunable gap qubit. So this variety of types of qubits after 20 years of development became rather large, and therefore there are different ways to classify those devices depending on their topology and characteristic parameters such as Josephson energy, charging energy, and the inductive energy of the loop. Again, I told you, I showed you already this formula that we discuss here. Transmon, which has zero inductive energy. We discussed the flux qubit, which has the inductive energy of the order of Josephson energy. And in the fluxonium, the inductance is larger. Therefore, the inductive energy, which has inductance in denominator here, inductive energy is quite small. So the Josephson energy dominates. And therefore, all these devices have somewhat different properties. Now, very interestingly, shunting the junction with the quantum junction with an array of junctions can be also used for the purpose of sort of sorting out superconducting qubits. And there is a paper, I think it has been published in 2021. I didn't update the reference here, from MIT group, actually proposing a more general kind of view on the flux qubits. So in flux qubits, one can vary different parameters. One can vary number of junctions, which is used for forming the inductance. One can vary the area of the small junction, of the quantum junction, by changing its Josephson energy. One can play with the shunting capacitance moving along this axis. And one can also play with the ratio of the Josephson inductance of the quantum junction to the inductance introduced by series array of junctions. And this all has effect on the characteristic coherence times. It also has effect on the characteristic frequency and so forth. So in this picture, one can see this kind of carousel as a starting point is a Cooper-Pea box charge qubit. Then one goes to transmon by increasing the capacitance. And then by adding junctions in parallel, one goes to C-shunted flux qubit, and then to fluxonium by making the number of junctions even larger. And then by going back to, by avoiding this capacitance, one goes back to the generic flux qubit, which we already discussed also, and sort of move this this whole circle of varying the parameters. But in all this circle, there are these characteristic parameters such as the junction capacitance and inductance and critical current, the shunting inductance, and then factor gamma is the factor by which the area of every larger junction in this array is larger than the area of the smaller junction, which is sitting here. And by playing with this factor gamma and the number of junctions, one can also meet a particular goal, for example, satisfying the condition of having positive anharmonicity, which, as I said, is relevant for a number of applications. So more generally speaking, one can take this generalized flux qubits. There is even a name for it, G-flux qubits, generalized flux qubit, and write the Hamiltonian such that one, of course, has the flux quantization condition of E is the external flux determined by the magnetic field which is applied, and then one adds into the inductance the cosine associated with the larger Josephson junctions. So this by making the junctions connected in series, the inductance increases. So this is a factor of n, And since the phase drop on these junctions, on each of the junction becomes smaller, then this cosine has phi over n here. So there is effective charging energy, effective qubit capacitance, which comes as a sum of the all the capacitances, the junction, the shunting capacitance, the capacitance of the larger junctions, and capacitance of the gate, which is being used for controlling eventually the qubit. So making this Hamiltonian in the writing this Hamiltonian in noise insensitive point, which means the half flux quantum applied to the loop, and expanding up to the second order term, one gets the formula which is similar to this potential of the which we discussed already for the fluxonium, but now it has the factor of plus inside the power of 4. And it turns out that actually one can make the parameter such that the factor in front of the power 2 can be made to 0. So you have flux of fluxonium qubit if this factor gamma is smaller than n, but larger than 1. You are in the limit of transmon qubit and make Josephson plasma-like oscillations if this factor gamma is larger than n is the number of light junctions. However, if you have gamma exactly equal to n, then this coefficient in front of the power 2 term is cancelled to 0, and you're left with the power 4 term. Power 4 term is sort of moving from a harmonic potential into the rectangular box potential. So it's the first step that you are getting more flat bottom and then steep rising edges. And as you know, in the box, quantization in the box, in one-dimensional box, gives you the energy levels which are not equidistant, of course, but the anharmonicity is strongly positive. Here in the power 4, anharmonicity is there, and it's actually also positive. So in difference from harmonic oscillator, which has zero harmonicity, of course, you go from soft harmonicity, which is a cosine potential, to another soft harmonicity, which has a different sign in the quartic potential. Quartic is potential of power 4. And this has really a significant advantage. So this is again the illustration. So if you're in the transmon regime, then you are having the slightly negative harmonicity. So this relative harmonicity is A divided by frequency of 0, 1. It's negative. So it's 1, 2 minus 0, 1, because 1, 2 is smaller than 0, 1. It's A is negative, and therefore it corresponds here to transmon. If you go to flux qubit, then harmonicity is strongly positive. But it requires, of course, then reaching the parameter such that the gamma over n is smaller than 1. However, if you go to this condition that gamma divided by n is actually equal to 1, then harmonicity is there, and it's slightly positive. So the realization of this regime is actually very, sorry, it's a different direction. It has multiple advantages, which I probably will not have time to discuss in detail, but just to give you an example, this quarton qubit, which can be used as a complementary qubit with transmon, is shown here. It contains only few Josephson junctions. In a way, one can think of this anharmonicity. This idea came into my mind now when telling you about that. One can think of this as a complementary pair of transistors. So if you have NPN transistor and PNP transistor, then you can make a device very symmetric, and combining those two actually makes the amplifier much more linear and much more practically useful than amplifier made of transistors of particular polarity. Now, here you basically combine two devices of opposite harmonicity, transmon and this quarton qubit, and this actually makes the schematics also much more convenient. On this plot, you see the parameter plane of qubit frequency and harmonicity versus qubit frequency for different devices. And typically, Fluxonium devices are all here. So the qubit frequency is quite low and harmonicity is quite high. But transmons, they're all down here. So transmons from IBM and from Google, they're all in here. And you see all this range, very interesting range of frequencies with significant harmonicity is not covered by anything. So basically, it only has C-shunted flux qubit from MIT, which is here. But then Quarton devices, they will be all in between. This is a new area which is still unexplored. It's still unexplored in terms of the robustness of the qubit manipulation, coherence, accuracy of gates, and so forth. So there is a lot of applied research going all around the world these days, somewhere in that region. And that's where I believe a lot of interesting physics will appear in the coming few years. So this is again this plot which I described, and this is a generalized flux qubit picture. A is the anharmonicity. So if you move along these different axes, then you reach different parameters which can be advantages for operation of the qubits, which you haven't had. So this is a summary of the lecture about flux qubits, Fluxonium qubits, which I had today. I had a few slides more than I showed before the break. So the Fluxonium is a qubit with extremely large nonlinearity. Compared to Transmon, it has this advantage of having very fast gates. Moreover, it has very low frequency that makes it possible to manipulate the quantum states of Fluxonium by directly digitally synthesized signal using arbitrary waveform generators, conventional devices. Now, the inductance of Fluxonium can have very high impedance at high frequencies, even larger than quantum resistance at frequencies of transitions between these levels, the energy levels. In this case, it's called superinductance, and it has also very interesting physics, which we will not have time to cover completely, but you can look up superinductance on web and find something interesting to read if you're interested. Optimization of qubit design leads to generalization of flux qubits and Fluxonium qubits in the so-called G-flux qubit. And it may be a very good candidate to replace transmons in the future, or being combined with transmons in circuits where errors can be minimized by having different sign of the harmonicity in participating pairs of qubits. Any questions to this lecture or last slides which you didn't ask yet? Please. Есть ли вопросы?
Ну, возможно, у меня есть вопрос. Да. Когда мы рассматриваем обобщенный как раз кубит, как раз когда мы хотим оптимизировать как-то его дизайн, и до этого, когда мы рассматривали флюксониум, у нас всегда наши джозефсоновские переходы не маленькие, а вот когда они стопкой стоят, они все одинаковые. Это чисто из технических соображений, или почему там нельзя их как-то модулировать, делать разными, предположим, менять через один?
Чисто технически, чтобы не усложнять, сделано просто. Но вот сейчас у меня в группе в Карлсруhe, например, мы работаем над именно стопками. То есть джозефсоновские переходы, которые объединены в цепочку не в горизонтальном направлении на подложке, а в вертикальном. Мы делаем многослойные джозефсоновские переходы, тем самым минимизируя емкость по отношению к окружению. И в этом случае нужно сначала перейти с нижнего электрода на верхний, а потом с верхнего на нижний. Да, получается две стопки, которые внутри себя каждая одинаково, но они соединены довольно большим электродом с большой индуктивностью. То есть это тоже получается, значит, неоднородный массив. То есть ответ на ваш вопрос, на самом деле, чтобы не усложнять, пока делалось вот так. Наверное, когда люди поймут, что усложнение может принести какие-то полезные результаты, так сказать, тогда вот на это пойдут. Пока еще до этого дело не дошло. Пока больше удается разбираться в всякой интересной физике, а не совсем еще такие уж совсем брутальные инженерные вещи делать.
Понятно, спасибо.
Конечно. Ага. Зависит от Насти и от вас. Но он точно будет, значит, после 6 января. Вот. Значит, поскольку на следующей неделе у меня последние 2 лекции будут, вот, ну, вам нужно будет время подготовиться, я просто буду не способен принять у вас экзамен после 19-го. Вот, то есть до 19-го, ну, это ошибка. То есть это Настя должна уточнить, мы с ней это обсуждали, вот, после Нового года будет экзамен. Ну, конкретную дату, я думаю, что подберет она так, чтобы было удобно для вас. Ладно, хорошо, будем двигаться дальше, да? Давайте. Тогда сейчас я расшарю слайды другой лекции. Вот. Вторая сегодняшняя лекция будет посвящена вентилям, который по-английски называется гейты. Угу. Видно, да? Вот, хорошо, давайте двигаться дальше. Значит, today we'll talk about single and two-qubit gates. And this picture shows some examples of two-qubit gates, which we are going to discuss at the second part of the lecture. Maybe we'll leave some of the material for the next week. I still have to see how to pack it more convenient for you, logically connected. So today we'll discuss qubit manipulation and qubit gates. Next week we'll discuss also the effects due to the coherence and the qubit readout with some of the news of the development in this area worldwide. Will be the last lecture next week. So you know that for making the quantum computing possible, one has to be able to make single qubit gates and at least one two-qubit gate. But at least means that it doesn't really mean effective computation. This means that you could basically do any type of algorithm with a single two-qubit gate coupled to a few single qubit gates, with the two-qubit gates coupled to the single qubit gates. But you need to combine, of course, all of them and then make the whole thing optimal by eventually using some more convenient two-qubit gates. So let's first talk about single qubit gates. Classical gates of a classical computer are shown here. These are the Boolean logic gates, something you know, of course, from the story about computing and electronics. So there could be simple gates like not simply inversion from 0 to 1 or 1 to 0. Now there is a gate which is not reversible, which is a gate AND and gate OR. And in this case, you apply two inputs to the gate and you get particular result according to the table shown here in the on the right. Now, there are also other gates which are all non-reversible, more exotic. This is NAND and NOR and XOR and so forth. All these gates are existing in modern computing circuits operating with classical computers. Now, in quantum computing, we operate with states of two-level systems, states of qubits, which are determined by two complex numbers, alpha and beta, which we could visualize on the Bloch sphere. Now, manipulation of these states is achieved by making unitary transformations. Unitary transformation means that you basically use unitary matrices to go from state 1 to state 2. And in this case, we move basically in In Hilbert space, for single qubit gates, we just have two-dimensional Hilbert space. And for n qubit gates, we have, of course, 2 in the power n dimensional Hilbert space. So if you have 2 qubit gates, then basically our dimensionality of the Hilbert space is 4. And the compilation of the path in the Hilbert space from point A to point B in Hilbert space for many qubits is simply done formally by applying those single qubit gates and 2 qubit gates. In principle, one can apply multiple qubit gates, and actually there is a whole direction in quantum computing now with quantum multi-qubit gates, which makes, of course, the approach not simple, since exact formulas are very seldom to find in such a complex problem of traveling in a complex Hilbert space from point A to point B. Nevertheless, doing the conventional approach makes the so-called universal quantum computing possible. And this requires, as I said, single qubit gates and at least one 2 qubit gate. Now, single qubit gates are basically rotations on the Bloch sphere. So if you start from a particular state and then multiply it by Pauli matrix, then which is a matrix 2 by 2 for a 2-level system, then basically you describe a rotation in the Hilbert space. And there are rotations around x-axis, y-axis, and z-axis described by these matrices, which you should know from Pauli matrix formalism describing spin 1/2 particles. The popular gate in qubits is the so-called Hadamard gate, which is this one, which can be then applied to arbitrary state, and then basically it inverses the coefficients in front of 0 and 1. So if you apply this state to not inverse, it rotates from 0 to a superposition of 0 and 1, and if you apply it to superposition state, rotates to one of the eigenstates. Now, some of the examples are shown here, like this applying X gate. Basically, it inverses the alpha and beta coefficients in front of 0 and 1. If you apply Hadamard gate to this state, you get the sign instead of minus, sign plus, and so forth. For 0, you get minus, and for 1, you get plus, and so forth. So now the table summarizing the single qubit gates is shown here, and you have again this matrix representation, and also corresponding jargon which people use, or notation which people use to describe the algorithms. Of course, there is a lot of work done nowadays in the field of quantum algorithms. We are not going to discuss that at all. But as an example, you see that every gate basically rotates the vector on the Bloch sphere. Now, how to do it? You apply typically, you manipulate the qubit by microwave pulses. You apply microwave at the frequency of transition between the energy levels of the qubit, between 0 and 1. And then if you apply continuous microwave, initially the qubit is at 0 state, you apply continuous microwave, qubit will undergo Rabi rotations between 0 and 1, and they will continue forever. Forever means until the qubit becomes decoherent, until the moment when coupling of the qubit to the environment destroy the initial information about the qubit state, so that we will measure it. Basically, it will be 50% probability of 0, 50% probability of 1 in the absence of relaxation. And in the presence of relaxation, we will relax down to the lower energy state. These Rabi oscillations are shown here. If one detunes from the resonance, you see the Rabi oscillation frequencies increases. And basically, the formula for the Rabi oscillation is proportional to the amplitude of the driving field. So larger is the amplitude, larger is the frequency of the oscillations. And if you detune from the resonance, then your frequency of Rabi oscillations is a square root of the amplitude of the driving field square plus the square of the detuning from the resonance, which means like detune from this green line to, for example, 4.82 means detuning of roughly 7 megahertz away from the resonance. Now, if one cuts like half a period of the Rabi oscillations, then you go from state 0 to 1, and this is exactly what is called pi pulse. And this will be a pulse which you apply on the qubit to bring to make rotations, like for operation, for example, not. Now, depending on the phase of this driving field, you can rotate around different axes. And this phase is not obvious, it's always determined relative to the initial state, relative to the initial phase of the pulses, which you apply after another. If you apply twice shorter pulses, which are called pi over 2 pulses, then you basically prepare the superposition state of 0 and 1 if you start from one of them. And then at 0 detuning, there will be no oscillations. But if you detune from the resonance, then you will see these Ramsey fringes. And this is the free precession decay type oscillations, which occur due to the change of the accumulation of the phase by detuned driving in the rotation of a qubit around in the equatorial plane on the Bloch sphere. That's something we already discussed. Now let's make it a bit more formal. The rotations, as I said, can be chosen as rotation around different axes by choosing the phases of the initial pulses. And the rotations around X, Y, and Z can be visualized on the Bloch sphere like that, and then I describe by this matrix elements. So all what we do with transmode qubits, we apply microwave signals at resonance frequency of the qubit, and then we apply pulses of these microwaves, being able to change their amplitude and phase. And by doing that, we basically can do arbitrary rotations on the Bloch sphere, which means implement different single qubit gates. Now, an important question, how we do it technically. And that's something which is not so obvious. Transmode qubits, for example, they have the transition frequency in a few gigahertz range. Synthesizing a signal in this few gigahertz range is technically not that simple. It became a lot simpler in the last, let's say, 10 to 20 years with the development of the conventional communication using, for example, cell phone communication and satellite communication. When you have a cell phone in your pocket, then you have basically a device which converts the frequency received from the external antenna into the quadratures of the reference signal, which means that you always up convert and down convert the signals from particular frequency down to low frequency range of the intermediate frequency. So the conventional heterodyne scheme of sending and receiving radio signals is using a nonlinear element, a mixer, in combination with a local oscillator. And if you apply a local oscillator to a mixer, and then you add the intermediate frequency tone or intermediate frequency digital profile, this profile or tone is being, as people call, up converted. So it shifts in frequency relative from 0 to the, now the 0 becomes the local oscillator frequency. And in that frequency range, one can basically manipulate the signals. It will be ideal, of course, if we can directly digitize the signals, generate basically the signals directly, but the semiconductor electronics is not that fast yet, and it may occur in 6G, but didn't occur yet in 5G. So what people basically use nowadays, they use a device which is called mixer, which has 4 ports. This is the IQ mixer. Some mixers have 3 ports, but I will explain exactly what the IQ mixer is. It has a local oscillator signal, which is coming to the local oscillator port. This is a continuous signal. It's not a pulse, it's a continuous signal, basically. Then it has 2 ports, which are called, which are both intermediate frequency ports, but shifted by the phase in 90 degrees. So means that they modulate the local oscillator frequency with 90 degrees phase shift. And these signals, which are in the range below 1 gigahertz, are being generated digitally by arbitrary waveform generator, and then on I quadrature it will go to left port, and the Q quadrature it will go to the right port. Of course, one can choose I and Q arbitrary, but more intuitive imagination is that I is the amplitude, Q is the phase. But of course, as you know, if you shift the AC signal by 90 degrees, then what was the amplitude becomes the phase, and what was the phase becomes the amplitude. So in a way, it's in the phase space, showing the vector of the signal, such that it starts from 0, has the amplitude of the wave transmitted, and then the phase is associated with the orientation of this vector around the origin. So if the phase is preserved, then it's actually pointing in particular direction. And here we basically project the signal on two different orthogonal directions, on I and Q, which can be amplitude and phase, or can be any combination of amplitude and phase shifted by 90 degrees. And once you have these intermediate frequencies applied to the local oscillator continuous signal, this local oscillator basically cuts the profile such that it upconverts the two signals such that it will generate signals at the frequency of local oscillator plus the frequency of the arbitrary waveform signal and minus frequency of I-form signal. And by choosing a particular I and Q phases, one can do the so-called single sideband conversion. For example, one can adjust the amplitude on the phase such that one can suppress the red tone and leave only blue tone above the local oscillator, or can suppress the blue tone and leave only the red tone. Now, this technique is a standard for any type of modern communication. Basically, you're getting here the driving frequency, which will be the sum, as I said, of the local oscillator, sum of the difference of local oscillator and the arbitrary waveform generator frequency. Now, imagine that you have now rectangular pulses here. So the simplest thing which arbitrary waveform generator can do, it will cut for you rectangular pulses. So when you have a rectangular pulse, then the profile of your driving tone is going to be changing very sharp. So it was nothing, and then sharply you start oscillating, and then you sharply cut. Obviously, if you make a Fourier transform of the rectangular profile, you get all the Fraunhofer tones, you get all the subtones in the Fourier space, which means that you generate a lot of unwanted frequencies. And the only convenient profile which you could do to be able to have a smooth representation in the frequency space is to generate pulses which will be modulated by the Gaussian profile. If you have a Gaussian profile and you Fourier transform the Gaussian profile, you get again the Gaussian. So this is really the power of that particular profile. And it turns out actually that most precise gates, the most high fidelity gates, which have very tiny errors, can be achieved by using Gaussian profiles for the amplitude and using the derivative of the Gaussian profile for the phase. I think I have the next slide. Yes, this one exactly, yeah. So you see, this is the so-called precision manipulation, precise manipulation of qubits. The problem here is that we manipulate state 0 and 1s. But if you have some unwanted frequency components in the signal, some frequency components which will be not exactly 0, 1, but will be shifted from 0, 1, you will unavoidably excite the second excited state, which is unharmonic, because unharmonicity is quite small for the transmon. Therefore, you need to make really this manipulation very, very carefully, and you make it basically by using the Gaussian profile for the I input of the mixer. It turns out that actually starting this Gaussian profile smoothly requires a particular trajectory on the Bloch sphere. This is the sharp Gaussian profile with no modulation on Q, and then you see that you go from one point to another, and your error is quite large. But if you delay a little bit this motion, and then you speed it up before the end, then you can make the path on the Bloch sphere very, very precise by using this optimized profile. And this requires basically having the Gaussian profile for the I and the derivative of the Gaussian for the Q. One can show this pretty exactly mathematically. There is a so-called optimal control theory applied to quantum systems. There is a lot of work done around the world there. Most of it is actually not being published anymore because it's know-how of the companies which optimize the quantum computing gates. But for you just to know that basically DRAC means derivative reduction by adiabatic gate, means using Gaussian pulses and derivative of the Gaussian pulses to control the qubit trajectories on the Bloch sphere. Now, what is the IQ mixer? I just told you that it has the amplitude and the phase, but in fact, it's nothing else as the device shown here. So it has actually two mixers in one. And every mixer has a local oscillator input and RF input. They are exchangeable. So basically, it's a device which can be used as a modulator or as a mixer. For example, one can use local oscillator to make the particular profile at the output. So this arrow will be reversed here. And that's what I showed you in the previous slide. So this is the way of using the mixer as a modulator. However, the mixer is a device which actually is designed initially to mix two high-frequency signals. One is the local oscillator. The other one is the signal from your antenna, for example, iPhone antenna, which you have in your pocket. And then, if the local oscillator frequency at the carrier frequency is mixed with the incoming signal, it generates two quadratures of the signal. It generates I and Q. Q is simply the same kind of wave, which is mixed with the phase shift of pi over 2, shift of 90 degrees. In this case, you have both. You have projections now of your signal, both on the horizontal axis and on the vertical axis. So you have both information about the amplitude and the phase. And then, depending where you are in the amplitude and phase, if you imagine the vector of the wave rotating around the origin, if you change the phase by 2 pi, then you pass all the points with this vector. Now I'm talking not about the Bloch vector, but about the state of the wave with particular amplitude and the phase of the carrier. Then one can encode different points in IQ space in different signals, and this is what is done in the cell phone communication when you have different users talking on different quadratures for the same carrier frequencies. So similarly, one can encode information in different quadratures, having both information in amplitude and phase. But the IQ mixer is simply a combination of two mixers, one of them shifted 90 degrees phase, and then either down converted for mixing or up converted for modulator. Now, single qubit gates have the purpose of implement different rotations. And this is an illustration for that if you do the pi pulse, you are end up in somewhere here. If you do pi over 2 pulse, you end somewhere here. And then depending on the detuning of the driving frequency from the resonance frequency, one can have additional phase accumulated if desired. I think I will skip that. This is a minor detail repetition of the previous slide. Now, interestingly, if you want to rotate around z-axis, basically you prepare some state on the Bloch vector on the equatorial plane, and you want to rotate it around. This is most easily achieved by modifying the critical current of the junction for transmon qubit, because it modifies the energy level separation in the Hamiltonian. And modifying the energy level separation comes automatically into the exponent of the phase of the quantum system, and basically you have a rotation around z-axis when you move around the equatorial plane of the Bloch sphere. So single qubit gates are very simple, and one can, as I said, represent them by 2x2 matrices, and there is a variety of them. One can, in principle, describe any rotation on the Bloch spheres, combination of single qubit gates, or introduce some crazy qubit gates, depending on the taste. And then decompile desired rotation into combination of those single qubit gates. Now, 2 qubit gates are more tricky. First thing to say that both single qubit gates and 2 qubit gates are different from conventional logic by the fact that they are described by unitary matrices. And that means that they are time reversible. So quantum computing is a reversible computing. Ideally, if you have no decoherence, then it's reversible computing. While the conventional logic is non-reversible. And you know that if you have 2 inputs for the AND gate, classical gate, then you lose the information about the state you started. So basically, you lose the information in terms of entropy, which is due to the destructive nature of this gate. You destroy the information and you pay the price of Boltzmann constant logarithm 2. If you want to read about reversible computing, look up the paper of Landauer around 1960. So back to the 2 qubit gates. So the most popular and so to say celebrated 2 qubit gates is the CNOT gate. The CNOT gate is a very simple gate, which we already discussed in one of the first lectures. It makes the target qubit rotate if the control qubit is in the state 1. So if the control qubit is in the state 1, then the target qubit changes its state. So if you start from 0, 0, it's 0, 0. Control qubit is in the state 0. If it's in the state 0, 1, first qubit is control qubit, then the result is state 0, 1. But if the control qubit is 1, then the target qubit, which is the second one, changes the state from 0 to 1. And if the control qubit is in the state 1 and the target qubit is in the state 1, then the resulting state is 1, 0. So one can easily see that this kind of gate is described by this kind of matrix. Now we deal with a 4-dimensional Hilbert space, so it's a matrix 4 by 4. And there are also other types of gates, so-called C-phase gate, which is described, also popular gate described by this matrix. But in principle, one can also have some gates which will have some arbitrary angle of rotation around particular axis in 4-dimensional Hilbert space. Now, ideal 2 qubit gate requires that you need to apply an operator acting on the qubit only when you want. And if you want to apply 2 qubit gates, you only do it when you want. So you would like to have the following properties of the 2 qubit gates. You want to have this gate either on or off. So if you don't want to have this gate, it has to be switched off. You need some kind of switch for that. You don't want to introduce any other parasitic coupling, so dephasing due to applying the gates. You, of course, do not want to have any leakage into non-computational states. You want to have really these gates as simple as possible and very, very robust. And satisfying these requirements is not easy at all. So this makes the whole complication of qubit designs and practical gates when it goes to practical implementation of superconducting quantum computers. By the way, any questions to single qubit gates? Okay, you all know this. That's very good. Let's move on. So this is CZ gate. There is another popular gate which is called swap gate, which swaps the states of 2 qubits, which is described by this matrix here. And of course, the number of gates can grow very easily. You can apply any complicated matrices here, but simply they are not that practical to be implemented in the pure form. Now, to make 2 qubit gates, we need to couple qubits. And this coupling can be achieved in different ways. For example, we can simply take 2 transmons and put a capacitor between them. This will be a direct capacitive coupling. We could also make two inductively shunted transmons or two fluxonium qubits and couple them inductively. This is going to be again direct coupling, but now inductive coupling, not capacitive. But there is also a way to make the coupling indirect, and this involves something in between the qubits. And the advantage of that is that one can, in principle, make this coupling then tunable, such that you could make the coupling, switch the coupling off and switch the coupling on. How to do it is the next question, but one example is where the non-switchable coupling, where you have simply a cavity standing between the qubits. This is something similar to ion qubits, where you have different ions coupled by the modes, mechanical modes in the ion array, ion chain. Now, the other advantage of using the tunable coupling consistent, which is more complicated here. For example, one can use another qubit to couple two qubits left and right, to put the extra qubit between them. And this is actually a strategy which turned out to be very productive. This is a coupling scheme which is being used by Google in all their working quantum processors. So let's discuss briefly different versions of these couplers. Again, this slide shows a summary which I borrowed from this review 2.5 years ago. The first picture shows direct capacitive coupling of two transmons. This is capacitive coupling via a cavity, which is called a coupler here in this sense. This is an inductive coupling between either flux qubits or fluxonium qubits, and this is the inductive coupling via the coupler. So capacitive coupling has an advantage that it's a short range. It's also compatible with conventional signals, which are usually not currents, but rather voltages delivered by semiconductor devices. Semiconductor devices can have very high impedances, mostly manipulating with electric fields rather than magnetic fields. Magnetic coupling is more tricky because one has to observe the magnetic flux quantization in superconducting loops, which makes the design not simple. And therefore, magnetic coupling is strongly non-local. Magnetic fields, as you know, are generated by currents and not by charges, and there are no magnetic charges. Therefore, magnetic field is always generated such that field lines always close in themselves. Nevertheless, there are schemes of coupling the qubits inductively. The problem is that if you have many qubits on the chip, then inductive coupling is much longer range than electric coupling, and therefore you will unavoidably couple your pair of qubits which you want to couple together to other qubits which will be on the same chip. So basically you have to pay attention on the so-called crosstalk. Means that different pairs of qubits doing different jobs will talk to each other, will interact with each other when you manipulate only one pair and not pay attention on the other. And therefore one has to calibrate the multi-qubit circuits to avoid these crosstalks. It really becomes rather complicated. We'll talk about this when we discuss scaling up of the qubit circuits. Now, one of the first examples when multi-qubit gates were demonstrated was done with indirect coupling with transpon qubits. This was already more than 10 years ago, done in Yale by Leo Di Carlo, who actually moved since then to Europe, to Yale, sorry, to Delft University, excuse me. So in that experiment, which I have chosen here as an example, they had the setup for cavity QED. They had 4 transmon qubits. Okay, now they were reading out these transmon qubits via the cavity, and this cavity was having the formed by this little gap at this point and also at that point. And then each qubit was detuned from the cavity, and therefore, but at the same time, the qubit was coupled to the cavity capacitively. And it turns out that diagonalizing the full Hamiltonian of the system shows that one can swap the states of different qubits between themselves by generating virtual photons between them in the cavity, which has detuned the way such that the photon will actually not occur in the cavity at all, but will be effectively swapped through the cavity, through the capacitance of the cavity and the qubit capacitance to the cavity will be swapped between the qubits. So this interaction with these virtual photons is described by the standard circuit QED Hamiltonian, and actually it strongly depends on the coupling coefficient or coupling strength between the qubit and the cavity. Obviously, if you swap the excitation into the cavity from a qubit, and then you swap this excitation yet once more from the cavity to another qubit, then you have to sort of have the second order coupling between the qubits, because it will be not G but G square. And in this case, the two qubit gates are going to be very slow. This has, of course, an disadvantage of using this practically. Now, this is the James-Cummings Hamiltonian, which you already know. So it contains the excitations in the cavity, excitations in the qubit, and then the coupling of the qubit. Here, the fast rotating terms were dropped down, forming the James-Cummings approximation. And then this is the spectral lines measured in microwave spectrum of the system. So here you see the frequencies of qubits. Qubit 1 has the frequency Q, it was tunable. Qubit 2 has fixed frequency, qubit 3 has fixed frequency, and the cavity has also a fixed frequency. However, if you tune the qubit 1 in frequency, if you move it by moving, starting from here, you change the flux and you move it to higher frequency, then what you see is the qubit 2 has very strong interaction with the cavity. So the coupling was very, very strong. And of course, here the coupling strength is simply measured here by this gap. So as you see, it was almost a gigahertz, or half gigahertz here. And the second order coupling was observed to qubit 2 and qubit 3. And you see that nevertheless, there was avoided level crossing at the qubit 1 crossing with qubit 2, and avoided level crossing at the qubit 1 crossing with qubit 3. So qubit 4 was not operate here. So what was done in this particular experiment, they formed a 3-qubit analog of the Bell state, which is the so-called GHZ, Greenberg Horn-Zeilinger state of 3 entangled qubits, described by this this formula. This is the eigenstate consisting of 0, 0, 0 and 1, 1, 1 state. And this was prepared using the algorithm of rotations around y-axis and the corresponding 2 qubit gates between qubits. So two qubit gates were achieved simply by preparing, for example, the qubit 1 in the excited state, then tuning it to the frequency close to the frequency of qubit 2, and then simply waiting there. And then if you have a splitting here, let's say 10 megahertz, for example, if it's 10 megahertz, then once you prepare the state of the system, which does not correspond to the eigenstate of this new Hamiltonian corresponding to this interaction at this frequency, the state will evolve in time. It will not remain stationary, it will evolve in time. And that means that actually the qubit, the excitation, which was initially in the qubit 1, will be swapped in the qubit 2 after some time, and then swapped back after the same time. So this will be this kind of swap oscillations between the two qubits due to the preparation of the non-eigenstate of the Hamiltonian. And the frequency of this swap oscillations is simply the frequency of the splitting here, which is observed near my arrow here. So basically, you need to wait the time there, which is the half of the inverse frequency of the splitting, and then you will swap the excitation from qubit 1 to qubit 2. If you wait only half of this time, then basically you'll share the excitation between 1 and 2. But to stop these oscillations, you need to detune the qubit 1 away. In a very similar way, you could also manipulate qubit 1 and qubit 3. and so forth. And by doing the swap oscillations with qubit 1 and qubit 2 first, and then moving qubit 1 to qubit 3 next, you will basically form an entangled state of all 3 qubits after this particular manipulation. And this is more or less what was done in this plot here. Without going into detail, basically they achieved quite high fidelity of about 88%. So basically they had achieved the error rate about 12% during this manipulation. So now more practical are the 2 qubit gates which are achieved with tunable couplers. And here you have basically an idea which was brought up first by Google team, then also explored by other people. Now this particular study is the work of the MIT group led by William Oliver, published a few years ago. Now you have here a tunable qubit 1, which is this red part of the circuit, and then we have a tunable qubit 2, which is the blue part of the circuit. In between, here you have a qubit very similar to those two, which is operated as a tunable coupler. What means tunable coupler? If you change the magnetic flux applied to this black squid of the tunable coupler qubit, then you change the frequency of that qubit in a certain range. And if you combine the frequencies of qubits such that this coupler is detuned away from frequencies of both qubit 1 and qubit 2, then the coupling is effectively very small. While if you tune the qubit 2 in qubit in resonance, then the coupling becomes very, very strong on resonance, and basically the excitation can be quickly swapped between 1 and 2. Now, the picture to the right is the picture of the energy levels, which actually tells that there is an effective coupling between qubit 1 and 2, which is shown here by the coupling coefficient G12, which occurs through 3 capacitors. It occurs through the capacitance C1, which is just the geometric capacitance always present there, and it occurs through the capacitance C1 and C2C, which are 2 capacitors below. And the idea is, it's very, very, very clever. Pay attention now. The idea is that basically, imagine that you introduce here the coupling through the capacitance C1, 2. This coupling is always such that you induce here charges such that inducing positive charge on the left qubit of the first qubit, you will introduce negative charge on the right qubit. So in a way, this coupling is sort of negative capacitive coupling with, or if you want, it's with a phase of pi coupling between the oscillations into qubits. Now imagine that you bring the circuit, which is here in the middle, into resonance. You know that resonance means that the phase of the oscillations in the resonating circuit goes through a large phase shift exactly at the resonance. Below the resonance frequency, the oscillations are in phase with the driving signal, and above the resonance frequency, the oscillations are out of phase with the driving signal. That means that by tuning the resonance circuit either below or above the resonance, one can make this capacitive coupling either positive or negative. And the idea is basically to adjust the parameters such that this circuit is being tuned to positive coupling, compensates for the coupling of the capacitance C1, 2. And by choosing particular frequency of the oscillations in this qubit, not oscillations, of particular frequency of this qubit, because it's simply is operated here as an empty tank circuit, as a coupler, it's not populated at all. Doesn't have to be populated. One can basically tune the coupling coefficient, effective coupling coefficient, which consists of 2 paths. Above pass through C12 and below pass through C1C and C2C. One can make effective coupling equal to 0. So basically, having a direct capacitive coupling C12 and tunable coupler, one can make the coupling cancel a particular flux applied to this black qubit in the middle. Now the whole circuit is shown here below. So you see two qubits. They have both readout lines, and they have the control lines and so forth. The coupler does not have any readout line. We don't need to know its quantum state at all. We only manipulated frequency, and then the coupling is implemented in a clever form. Now, this is the Hamiltonian for coupling, for this coupling scheme between two qubits through a tunable coupler. Here you see two coupling channels, G12 and then G1, G2. And then you have three groups of terms in the Hamiltonian. You have two qubits with the coupler, you have qubit coupler coupling, and then you have qubit coupling, which has this G12 direct coupling between the qubits. Well, the whole math is quite complicated. It can be looked up if you're interested, but the effective coupling between states 1, 0 and 0, 1 of the two data qubits on the left and right is written here. It has this coefficient has now fixed coupling G12, then coupling G1 and G2. Then it has also the coupling associated with detuning of the qubits from the detuning of the coupler from the qubit frequencies, and also detuning of the qubits from each other. So these are the terms delta 1, delta 2, sigma 1, and sigma 2. So, and you see that it has some signs as plus and some signs as minus. And the trick is really to find a combination here so that one can make, under normal condition, this coupling switched off, such that this whole term actually, I mean, this term and this term, when they cancel each other. So this is looks complicated, but turned out to be doable, and that's what actually Google does all the time in their quantum circuit. This is again a bit more detailed, the same formulas, but now the resulting coupling strengths in megahertz calculated, and this is the coupler frequency, which is tuned by changing the magnetic flux in this loop. And you see that below 5.5 gigahertz frequency of the coupler, this coupling is negative, above it's positive, and exactly in the middle is exactly 0. And this is why the whole thing is actually working. So one makes a tunable coupler out of another qubit of tunable frequency. Now, the problem here, there are many problems here, of course, but the key problem is that this coupling does not completely remove the interaction between the qubits. Since the qubits are not ideal, they have also the second excited state. It turns out that due to the interaction between the second excited state of each qubit with the state 1, 1, when both qubits are excited, doing the gates becomes the gates become non-ideal. There is always the additional ZZ coupling, which is described by this formula here. I don't have time to go into detail. Actually, it's a whole big area of research, but it turns out that one can actually make this coupling either positive or negative depending on the anharmonicity of the qubit. And it turns out that if one combines a transmon qubit with the G-flux qubit of exactly the same in magnitude but opposite in sign and harmonicity, then one can basically cancel out this parasitic ZZ coupling. So parasitic ZZ coupling is something which is very bad because it generates so-called coherent errors. It's not the errors which are due to the loss of information in qubits, errors which are due to the coupling to the environment. These are errors which are always there, and they're intrinsic to these quantum systems, which are only approximately two-level systems. And therefore, for a long time, it was really a difficult problem to compensate for this ZZ coupling, but more recently, people learned how to do it, but nevertheless, it's not simple. Yet another example of the two-qubit gates is the two-qubit gates which can be achieved by coupling the qubits directly. This is the capacitive coupling between the qubits shown here, described by this Hamiltonian. This is the coupling of two qubits directly. And then here you see again the picture of the qubit levels when the qubits are tuned between different points. So here, the frequency of the qubit of the second qubit is fixed, and the state 0, 1 is having the frequency of about 4.6 gigahertz. Now the qubit, this is second qubit. The first qubit, when excited into its excited state, can be tuned then in frequency by magnetic flux, and then in the region where these frequencies cross, you already know this, there will be a swap gate. If you wait half a period, it will become square root of swap. Depending on the phase, it can be also called I swap. Actually, it's I swap if you discuss this directly in terms of matrices. And this is a possibility of making the I swap gate. At the same time, one can also use non-computational state of the system, the state 2-0, for implementing the C-phase gate. So as a result, the state 2-0 will be populated only during the gate itself, and then after the gate is finished, it will be empty again. So this interaction through the non-computational states is also kind of popular direction of implementing multi-qubit gates with superconducting qubits. So basically here, you have the 0-2 transition for superconducting qubit. This is the state 2 of the first qubit. This was the state 1. The orange and this lila violet curve is the state 2. And then the state 0-2 of the second qubit is around here. And then the state 1-1 of the coupled qubit system is basically a sum of the two frequencies. This is the sum of this frequency and that frequency. It's here, roughly. And then if you tune now the qubit tune qubit 1 again in its second excited state, it crosses with the state here. You see it has a crossing with the state of the 1-1. It has a crossing with the state 2-0. And basically by traveling to this point and back, one accumulates the phase and occupies the states in the four-dimensional Hilbert space such that a particular states will be finally occupied and entangled with initial state of the initial state of uncoupled qubit system. Well, all that is not simple. It's rather complicated, and studying a particular gate can take the whole seminar. So I'm not really in a position, unfortunately, to show you a lot of examples here. But as an illustration, this is the I swap gate, which is very simple, which I already discussed. That's where you go into swapping the excitation between first and second qubit by tuning the first qubit to the frequency of the second qubit. And this is what happens, how it describes by the matrices. It, of course, depends on the time standing here, which you wait at the point of avoid level crossing. But when you come to the point and you go away from this point, of course, there will be also additional errors, and one needs to measure those errors, calibrate for those errors, and then cancel them out in the final implemented gates. And there is a lot of work which is hidden here. So some of these things you could do analytically, some of this you cannot. Many of them you could solve by evolutional learning and even applying machine learning to making error-free single and two qubit gates. Simply by doing the measurement of the final state, one can make the gates much more efficient and learn from errors which occur during the way. I think I will skip that one. I want to mention something which is done only by one company so far, or maybe by two. I think by two. Both Rigetti and IBM. They have chosen different paths to couple qubits, and they use non-tunable qubits and apply gates using only microwaves. And here the idea is to use the fixed frequency coupler between two fixed frequency qubits. The qubits are not exactly the same frequencies. They have some frequencies which need to be learned from testing the circuit. And then one applies a particular combination of microwave tones, typically at the frequency of the so-called cross resonance, which means that the frequency of the difference between the frequencies of the two qubits. Without going into detail, I'll leave you with this picture here that you could do by applying this combinational tones. One can apply then to states of individual qubits and then do swap operations between 1 and 0 by applying these parametric gates. And also use some non-computational states like 2-0 by manipulating the system to arrive into state 1-1 and so forth. So this is a level structure of two coupled qubits, which by itself already is quite complicated. But believe this or not, really this works very well. And due to the simplicity of these gates, the progress with scaling up multi-qubit circuits on the side of IBM has been much quicker in the last years than it was happening with Google, which went to the tunable Kepler gates, which I described before. So it's again a bit some story of the of these parametric gates. So one can apply also gates to the virtual level or this unoccupied levels and so forth, and achieve by that efficient rotation. So this is the whole field which is being developed over the last, let's say, 6-7 years, and is also quite complex. And I think this multi-qubit gates can be a lecture course for itself, but for that you need to know really the background and also know a good reason why you want to know about that for. So this is a variety of 2-qubit gates, which some of them I addressed, some of them not. So this cross-resonance gate, which I described already just very briefly at the end. This is the I-swap, which we discussed quite detailed. This is CZ, also addressed in our lecture. B-swap was not discussed, but that's something which can be achieved by modulating the qubit coupling at particular frequency. So this is a table of the variety of the gates. I think I have some slides also about 2-qubit gates on IBM quantum processors and the graph structure for the qubit architecture, something which I'm not going to discuss here. Again, some references here on the papers and so forth. Of course, I'm not going to ask you details about 2-qubit gates at the final exam. This is just for you to have an idea how complex and how broad this whole field is, because of the variety of possible technical realizations. But of course, having an idea how 2-qubit gates are achieved in experiment, what they do and what are the complications on the way, that's a good thing to know when learning about solid-state quantum hardware. Okay, I'll stop at this point. I think I'm almost on time. Any questions, please? Пожалуйста, вопросы. Знаю, было непросто.
Сейчас. А можно еще раз? А как мы защищаем кубиты, условно, друг от дружки? Как мы защищаем, чтобы один кубит не влиял на другой, если они достаточно близко находятся?
Ну вот только вот таким вот трюком, вот такой вот схемой. Когда мы используем вот этот связующий черный кубит, вот, тогда, изменяя магнитный поток в нем, мы эффективную связь, которая состоит из непосредственной связи и перестраиваемой связи вот этой вот, мы ее суммарно меняем. И вот суммарный коэффициент связи, он нарисован здесь. Вот, это вот JDC. Это вот самый, этот же самый JDC в зависимости от частоты черного кубита. И вот вы видите, что эта связь, она имеет один знак с одной стороны от точки при 5 ГГц, другой знак при другой. Ровно в этой точке, когда мы подстроим магнитный поток в этом кубите так, чтобы он был вот именно здесь, связь равна ровно нулю. Вот. Это очень легко меряется, на самом деле, экспериментально, когда мы приготавливаем кубит 1 в возбужденном состоянии и просто ждем, насколько долго он будет перебрасываться вот сюда. Вот. То Ведь они же должны через эффективную связь делать вот эти своп-осцилляции. И оказывается, что вот именно в этой точке, когда вот частота вот ровно эта, связь равна нулю, и тогда состояние не перебрасывается, они полностью изолированы оказываются.
Ну, то есть, по факту нужно вот, так сказать, ставить вспомогательный кубит между любыми двумя парами.
Да, именно так. По-другому никак.
Просто, ну, то есть, вот этим вот вспомогательным кубитом мы можем по факту менять эффективную связь. Ну,
Да.
то есть мы же его можем настраивать, и мы можем как бы...
Да, мы можем, даже связь мы можем настраивать. То есть, если мы хотим включить, сделать двухкубитный гейт, мы можем этот кубит отвести сюда, например, или сюда. Понятно, что лучше его отвести сюда, потому что в этом случае связь будет больше, и этот вентиль произойдет, этот гейт произойдет за короткое время. Вот, поэтому мы должны, как говорят, калибровать каждую пару кубитов в процессоре. То есть, на самом деле, калибровка квантового процессора – это очень трудоемкая процедура, которая занимает долгие часы, дни и даже месяцы. Вот. И даже кто-то пошутил однажды, Джон Мартинес пошутил, что оптимизация рабочей точки квантового компьютера на сверхпроводниках требует квантового компьютера для ее оптимизации. Очень много параметров нужно учесть, и все вот эти вот кросстоки, то есть перекрестные взаимодействия нежелательные между разными парами кубитов, это все необходимо учитывать. Я вам об этом немножко расскажу чуть позже, в конце последней лекции.
Хорошо, ладно. Спасибо.
Еще вопросы, пожалуйста.
А сколько у нас в целом лекций осталось?
2. Завтра, через неделю, во вторник, у нас будет последняя двойная лекция.
Спасибо.
Угу. Хорошо, тогда спасибо вам за внимание. Увидимся через неделю. До свидания.
Спасибо.
Спасибо, всего доброго.
До свидания.